The Earth abounds with a variety of elements and compounds. In addition, we have seen different types of alloys, compounds and elements. To classify these substances based on their magnetic properties, let us discuss the basics of magnetic properties. We know that matter is made of atoms and atoms are made of electrons and nuclei. We have seen that a circulating electron in an atom has a magnetic moment. The resultant magnetic moment of an atom is the vector sum of the magnetic moments of all such circulating electrons in the atom. Here, the magnetic moments of these atoms in an object are randomly oriented and their net magnetic moment is 0. When the object is placed in an external magnetic field, the magnetic moments of the atoms are aligned partially or completely in the direction of the applied magnetic field. Then, the net magnetic moment of the object is in the direction of the external magnetic field. Thus, the net magnetic moment per unit volume is called magnetization or intensity of magnetization. That is, I is equal to m by v. The unit for intensity of magnetization is ampere per meter. Its dimensional formula is m0, L-1, T0, A1. When an object is placed in an external magnetic field, the total magnetic field inside the object is the sum of the applied magnetic field and the magnetic field due to the magnetization of the object. To discuss this more explicitly, let us consider a long current-carrying solenoid, where B0 is the magnetic field in the interior of the solenoid due to the current passing through it. When a magnetic material is inserted into the solenoid, the material gets magnetized. In such cases, the total magnetic field inside the material is the sum of magnetic field due to the current carrying solenoid and the magnetic field due to the magnetization of the material. That is, B is equal to B0 plus Bm, where B is the total magnetic field inside the material, B0 is the magnetic field due to the current carrying solenoid, and Bm is the magnetic field due to the magnetization of the material. Let this be equation 1. The magnetic field due to the magnetization of the material is directly proportional to its intensity of magnetization. That is, Bm is directly proportional to I. This equation can be further written as Bm is equal to mu0 into I, where mu0 is the magnetic permeability of vacuum. Let this be equation 2. Now let us introduce a new vector quantity called magnetic intensity, denoted by H, where H is equal to B by mu0 minus I. Let this be equation 3. The units and dimensions of magnetic intensity are the same as that of intensity of magnetization. That is, the SI unit of H is ampere per meter, and its dimensional formula is m0, L-1, T0, A1. On rearranging the terms in equation 3, we get the total magnetic field inside the material, B is equal to mu0 into I plus H. Let this be equation 4. Now, the total magnetic field inside the material is redefined in terms of I and H. That is, the external magnetic field applied on the material, represented by H, and the magnetic field due to the magnetization of the material, represented by I. The contribution due to the magnetization of the material I is influenced by factors such as the nature of the material to be magnetized and the applied magnetic field. It can be expressed as I is equal to chi into H. Let this be equation 5, where chi is a dimensionless quantity called magnetic susceptibility. It depends on the nature of the material, which represents the degree of magnetization in response to an external magnetic field. The value of magnetic susceptibility is small and positive for paramagnetic materials. It is small and negative for diamagnetic materials. Substituting equation 5 in equation 4, we get the total magnetic field inside the material B is equal to mu naught into chi H plus H. That is, B is equal to mu naught into 1 plus chi into H. Let this be equation 6. But the magnetic susceptibility and relative magnetic permeability are related as mu R is equal to 1 plus chi. Hence, in place of 1 plus chi, we can write mu R, and we can further write equation 6 as B is equal to mu naught into mu R into H. Let this be equation 7. We know that the relative magnetic permeability is the ratio of the magnetic permeability of the material to the magnetic permeability of vacuum. That is, mu R is equal to mu by mu naught. Then, mu is equal to mu naught into mu R. On substituting the magnetic permeability of the material, mu, in equation 7, we get the magnetic field as B is equal to mu H. Let this be equation 8. The three quantities, magnetic susceptibility, magnetic permeability, and relative magnetic permeability, are related to each other, and only one of them is independent. If one of these values is given, the other two values can be determined easily. Let us have a look at the magnetic susceptibility of some elements at 300 Kelvin given in the following table. Here, it can be seen that in the case of diamagnetic substances, the value of magnetic susceptibility is small and negative. And in the case of paramagnetic substances, the value of magnetic susceptibility is small and positive.